Planning, Power and Precision. Welcome back, and thank you for joining me. Statistical power, I'm deeply ambivalent about it. It only has meaning in the context of statistical significance testing, which I'm trying to avoid, and therefore I don't want to use power as a concept. But if you're going to use NHST, you really do need to consider and discuss statistical power. And I won't go through all the textbook stuff. Power is the probability that you'll reject, get significance, if there is a true effect of your specified target effect size. Now, if we don't use power, how do we plan our experiments? Well, the corresponding thing in the estimation world is precision for planning. And the idea is that we specify how wide a confidence interval we're prepared to accept, and then given that, we calculate how large an N we need to achieve confidence intervals no wider than that. And this is a strange concept maybe, or doing it is unfamiliar, and really only in the last few years have the theoretical developments been made easily accessible to allow us to do it. And that's only really in simple situations. Now, the word power is used ambiguously. Statistical power, which has a technical meaning, but also more loosely a sort of goodness of an experiment. And I want to separate out these two meanings of power because I don't want to use statistical power, but I do want a word for sort of goodness of experiment, and I've decided to use informativeness. Bit of a mouthful, but I still haven't come up with a better one. And so I want to discuss how we make our experiments very informative, because that really matters, and then how we plan them using precision. But first I'll just say a whisker about power. This is the power diagram, the distribution of our test statistic when the null is true, and then when the alternative is true, and if this is the value corresponding to our target effect size, then yellow area, plus an invisible area down there, is the power. And perhaps even without going into ESCI and playing with this, you can see that if you move this red distribution over a bit, then power gets quickly very much larger. So power, statistical power, depends critically on the target effect size. And we have a little bit about that in this article. I am going to say a little bit about statistical power. Let's take this example of the HEAT, the hot air awareness test, which I used in the first book. I made it up. And it has a mean in the population of 50, standard deviation of 20. And let's suppose we wanted to calculate statistical power when we had some effect size that's meaningful, and we judge in our situation to be 8 points on the HEAT, which is 8 over 20, which is delta, a population effect size of 0.4, standardized Cohen's d or Cohen's delta. And then we can go into the power pages of ESCI. And here we've got the power pages for two independent groups, each of size n. And we've set alpha 05, two-tail. We're using, we've highlighted the delta 0.5 true effect size. And if we had two samples of size 32, the power is 0.5. And I can vary sample size and see how power changes. I can also highlight different values of the population effect size. So that's 0.5. If I go up to 0.6, power jumps up to 0.66. If I go down to 0.4, it drops down to 0.35. And so you can play around a sensitivity analysis here. But usually, to get decent sort of power, 0.8, 0.9, you've either got to have a very large population effect size or a very big sample. That's the bad news of independent groups design. But we could go to the power paired page here, where we've got a single group. We're using, say, a pre-post design. We've specified rho, the population correlation between pre and post, and I've specified, perhaps slightly conservatively, 0.7. And even then, with a single group of 32 and a population effect size of 0.5, I've got a power of 0.94. So if I run that experiment and there is a true effect of 0.05 in the population, then I've got a 94% chance that I will get p less than 0.05. So this is very traditional sort of country for dealing with power, but it's the thing that ESCI does offer. So for an independent groups experiment, and in each group, I can play around with trading off the population effect size and the sample size and the power. But very often we have disappointing news, need large samples. But if I go to paired design, we set rho, the population correlation, and sometimes we get fairly encouraging news that the size of sample we need is not so bad, assuming, of course, that a paired design is appropriate for our situation. Ways to increase power will, of course, increase n, increase the target effect size, or increase alpha. If you set alpha, prepared to accept alpha 0.10, you'll get nice high power. I mean, these are very cheap and nasty ways to increase power. The fact that your experiment's got enormous power to find an effect that's enormous, not telling me anything at all. Or to put it slightly more positively, if you're going to make a statement about power, statistical power, you must specify what your target effect size is. So you say this experiment has power of 0.7 to detect a true effect, if it exists, of delta of 0.4 or 0.6 or whatever it is. And so unless that's specified, we don't know what's going on. And you can improve the experimental design or use better measures. They're things that actually improve informativeness as well, whereas these cheap and nasty manipulations don't, of course. G-Power is a wonderful gift from some German scientists to the world, wonderful software for calculating power, a free download from there. And so if you do want to do power calculations, certainly look at G-Power. Statistical power in psychology and a number of other disciplines has alas often been very low. And Cohen, 60 years ago, 50 years ago, published data showing that in many areas of psychology, average or median power to find a medium-sized effect, delta of 0.5, is only a coin toss. And 40, 50 years later, still in many cases, just about as bad. Deeply disappointing for Cohen that his message was heard to some extent. I'm sure a lot of people use his book and have heard about power, but we have not responded in the way he wanted, which was to act to improve our power, or at least we haven't done that sufficiently. My colleague Neil Thomason interviewed Cohen in New York 15 years ago or so, a few years before he died, and asked him, you chose to emphasise power as the thing that you advocated and put a lot of effort into. If you were doing it again, would you choose power once more? And Neil reports that Cohen actually said, no, I wouldn't. I choose confidence intervals. I choose to spend my effort advocating a switch to estimation. Now, he did advocate that switch, but he put most of his effort and put his effort in publishing his book into power rather than estimation. Another bad thing about power is post hoc power. You might say, well, how do I choose what target effect size I should specify for my power calculation? Well, choose something that makes sense in the research situation or some target you've got. Why don't I just do the experiment and use my obtained D in my power calculation? Well, the trouble with that is, that's post hoc power, calculate retrospectively. The trouble with that is, and you can simulate this easily in ESCI, the power you get merely reflects the size of your obtained D. And if you repeat this experiment a number of times, you'll just through random fluctuations get a large value of D and a large power. Then you'll get a medium and a medium, and a low, and it'll bounce around. So you look at a few of these and you quickly decide, well, these post hoc power values, they're just sort of telling me again what I already know, which is how big an effect I got in this experiment. So this has been devastatingly criticised, for example, in this famous paper in the American Statistician. And it really wouldn't be worth mentioning except that I understand some software, which will remain nameless, reports post hoc power. And this is the thing really to be alert to. If you get an analysis which includes a power value, then you have to ask, well, power for what effect size, for what target effect size? And if the software has come to you and said, well, look, I'll calculate your power if you like, but you've got to tell me what target effect size you need. And then you wish, and then you type it in and said, okay, in that case power is so-and-so. That's fine. But if you get power without some clear statement of what the target effect size is, alas, there's a fair chance you'll be given post hoc power. And that is a real cop-out by software publishers, so be alert to it and never use post hoc power. So let's get positive and think about good aspects of designing experiments. And here really I'm just inviting you to direct your attention to all the standard things in the experimental design books. How can we improve our experiments? Well, choose an experimental design to minimize error. Minimize measurement error. Choose better measures, measure a couple of times an average. Covariance, statistical control. Use bigger groups, maybe by sacrificing some of your manipulations so you can get bigger groups, bigger comparisons for the things that really matter to you. So many times I've sat through presentations by graduate students of work they propose to do that's beautifully logical and clear, wonderfully justified, nice, complicated factorial experiment. But alas, I sort of weep quietly in the back row thinking they're going to get random numbers. They just don't have the time, the resources, the participants to do this complicated a study. And so it's really worth a lot of effort to brainstorm ways to improve our experiments. And, you know, every book says this and everyone says this, but we don't do it. We don't do it sufficiently. So when thinking about power, okay, you can calculate things if you want, but the real message is it's worth a lot of time and effort to improve the informativeness of your studies. Do some extra piloting. Try and increase the effect size you're studying. Look at 6 therapy sessions, not 2. Hopefully that'll give a bigger effect. And every way you can to reduce error variability. And confidence intervals can help because they tell you what that variability is. And so if your goal is to shorten your confidence intervals, increase your precision, well, that is great. So let's move on to, yes, short is good, small is beautiful. Precision for planning. It's also known as accuracy in parameter estimation. Well, I don't care. PFP seems to be simpler, but there you go, precision for planning. Now, the idea is that we choose F, which sort of stands for fraction, and we want our MOE, the length of one arm of our confidence interval, to be no greater than F times sigma. So F is sort of in Cohen's D, Cohen's delta units. We'd like to finish up with a confidence interval no longer than plus or minus 0.3 sigma or 0.4 sigma. So here is our confidence interval with MOE being F times sigma. The trouble there is that I've had to put in expected MOE because we know that the length of confidence intervals bounce around because they're based on sample standard deviation typically. And so I can't give an absolute guarantee that my MOE will be this short. All I can say is that on average, in the long run, it'll be no longer than that. Unless I look at the new, the additional concept of assurance. And I can say, well, look, I'd like to be 99% sure that my MOE will be no longer than so-and-so. And we can do that. Okay, let's go to ESCI again and look at precision 2. So what we've got here is a graph of the sample size we need in order to get average MOE no more than 0.4, because I've set this cursor here on 0.4. And you may not be able to read, but it says 50 up here. So this is saying, okay, for two independent groups, if I have two groups of size 50, then on average, my confidence interval on the difference will be no greater than 0.4 times sigma. And so that's a useful approach, a useful piece of information to help you design your study. Okay, what about assurance? I can turn on, I can set here 99. I want 99% assurance. You can choose other values. And I get this pink curve. And this tells me that for two independent groups, each of size 65, my confidence interval with 99% chance on 99% of occasions, my confidence interval will be no longer than plus or minus 0.4 times MOE. So again, we've got reasonably discouraging news with two independent groups. Confidence intervals plus or minus 0.4 of Cohen's delta. That sort of seems pretty wide, doesn't it? Well, that's the way it is. And again, we can do better if we go to single sample. Now here I've, let's move this down to say 0.4 again. So here I've got paired experiment, paired data, a single group of size n, and I've again chosen target MOE on average no more than plus or minus 0.4 of sigma, and the answer is 17. So a single group of 17 will give me this short confidence interval. Of course, each participant has to be tested under both conditions, but still, there we go. And here I've specified rho, the population correlation between the pre and the post of 0.7. And if I put this up a bit, say to 0.8, well, even a group of 13 will do. If I want assurance, let's turn on the assurance curve. Oh, a bit higher, I need 21. So what's this saying? That if I have a paired experiment, single group size n, each participant tested in two conditions, and I'm looking for the confidence interval on the change, on the difference, then if I have a group size of 21, I've got a 99% chance my confidence interval will be no longer than 0.4 sigma. That's a bit of a mouthful, but that is the sort of logic and the sort of answer we need if we're going to do estimation. So this is a variation of what I did with two independent groups. We finish up with quite big numbers. For assurance, even more. Such large n, even with f of 0.4. But for the paired experiment, if we assume rho is 0.7, that population correlation, then n is 17, much more encouraging if that design is appropriate in that case. So ESCI can do these calculations for you. This is not yet widely used, but I think has enormous potential and definitely a thing to watch out for. It would be a great project to write the equivalent software to GPower for precision for planning, so that you can go in with your factorial design, your correlational design, your SEM, whatever, and specify what confidence interval width you're prepared to accept, and then it should give you the sample sizes. And these precision for power calculations should replace statistical power calculations for your applications for funding and for ethics approval. So you can predict what these conclusions are going to be. If you are using NHST, then take power seriously. Choose a meaningful target effect size, don't use post hoc power. Whatever you're doing, make great efforts to maximize informativeness. And precision is the length of one arm of a confidence interval, that's our MOE, and that's in effect size units. So it's natural if you're working with estimates and effect sizes to keep thinking in effect size units and to do your planning also thinking in effect size units, whether it's milliseconds or points on a scale or whatever. And so precision for planning, the next big thing, let us hope. I'm going to guess that we've got time for 1.5 questions. Who would like to ask one of them? Down the front here.
So given that, it seems like sometimes testing the same participants twice could actually be more useful than doubling your sample size. Is that correct?
That's a very interesting observation, and I'm not sure there is a universal answer to that. It will depend on the reliability of the test and various other things. But one of the things I think I said on the informativeness page was we want to reduce error variability. And measurement error is, I won't say part of that, but it's part of the problem. And so we want to reduce measurement error. And you're quite right that measuring twice and averaging, or measuring 6 times and averaging, can be a very useful strategy. We've got to, of course, be careful about learning and fatigue and so on and so on. But I think it's one intuition that beginning researchers have not yet developed, and that is, okay, I'd prefer to test 40 than 30 people, or 60 than 30, but you might get just as much bang if you did the 30, but you were just so careful and controlled about getting everything about the procedure and the instructions and the stimuli and so on as uniform as possible. Bring them all up to the same level of practice, or other sorts of things that reduce the variability somehow and allowed you to have a more informative experiment. And so really here I'm just urging you to raise your consciousness about all those things, which I'm sure you know about anyway. Let's have one last question.
Hi, just a quick question. So in this precision for planning approach, you are trying to find basically the number of subjects that are required to reach a certain MOE or a certain margin of error. But in some ways, the beauty of this approach is to really focus on the confidence interval and use it to use your confidence interval to interpret your data or to get your effect size. So in some sense, aren't you constraining the very thing that you're trying to interpret later on by planning sort of what I guess.
You're asking, okay, as I'm planning the study, I'm thinking ahead and saying, I'm going to get a confidence interval on that difference between the reaction times or whatever. Of course, I don't know what it's going to be, but I want to set my study up so that I've got a decent chance or a 99% chance that it won't be more than so-and-so. Now, it seems to me this does not suffer from the problem of post hoc power. Post hoc power, we wait till we get it, then we calculate back. There's actually a logical problem there too. But here we're simply having continuity of thinking. Before the experiment, we're thinking in terms of the precision of our final result. We do the experiment, and of course we get a certain confidence interval width, and let's hope it's nice and short, but if it's very long, well then maybe we have to go back and rethink some of our assumptions, or the delta we use, the sigma we use, the population standard deviation we use in our calculations. And but I think the continuity is more important than the possible danger you point to. The continuity that as we think about planning and as we interpret our results, we're doing the same sort of thing. We're looking at the same thing, a confidence interval with a certain precision, and we're thinking about it in terms of milliseconds and the importance of so many milliseconds and how helpful it would be to us if we had an estimate plus or minus so many milliseconds. So, section 5 on power informatives, designing good experiments. We're going to go on to bring things together. That's what meta-analysis does, meta-analysis and meta-analytic thinking. So thank you for your attention to precision for planning.